Good afternoon. Today we are going to see the last part of these trusses where we have to design the member. Actually, if we will go through this, then we have this is little bit lengthy as compared to your gantry girder. So now we will have again repeat it. Please go through these 3 videos and see clearly IS code clauses. I am not going to repeat in this video, and then it becomes easy for you to solve the problem in examination. And these videos are in design of steel structures term work. So now we have calculated forces in members. Now we have to go for combinations, and after combinations we have designed the members L7 L8 U7 L8 we have to again design, and L7 U7 we have equal to 0. This L7 U7. So we have to design these two members. Now we have already seen we have forces in members. If we will see, we have in L8 U7 dead load minus sign shows compression. This is also compression, and we have due to wind load we have tension. This is actually principal rafter. And in principal rafter we have compression due to dead and live load, and tension due to wind load. And this is time member, and in time member we have tension due to dead and live load and compression due to wind load. So we have this 1.5 dead load plus wind load as minus compression, and this is plus, so we have tension. Then we have these two, again we have plus, so we have this as tension and this should be minus. We have this as compression. That means what we have to design now, we have to design L8 U7 for force 118.95 kilonewton, and that is compression. And then we have to design other member, we have L8 L7, that is for force 113.94 kilonewton, and this is for tension. So now we will first design L8 U7. Now in this L8 U7 we have to go compression member. So we know we have to go to table 9A B C D, and now we will go with 9A B C D. So length of member, so we have this length, this is, you can see this member, so we have this U7 L8, and this U7 L8, this member we have this length 2.61 meter. So U7 L8, and then we will go with, so we have length of member 2610 millimeter. Then we have area of the member, sorry, we have this length. Then we have to assume compressive stress, and accordingly we have to select this section. So assume FCD, and let us, we will assume this value of FCD, that is equal to 90 Newton per mm square. Now considering this value 90, we will get area required is equal to P upon FCD. Now we know value of P is 118.95 into 10 raised to 3 upon 90. So we have 118.95 into 1000 divided by 90. Then we have this value 1321.67. Now this is double angle. We have principal rafter and main type, both are double angle section. Therefore, area required for single angle 1321.67 upon 2, and we have this value that is equal to 660.83. Now we will consider angle. Select 65, 65, 6. We have RZZ is 19.6 millimeters and A 744 millimeters square. So now we will have KL upon RYY. So actually we have RZZ, R minimum, not RYY, and minimum we have RZZ. Now as we have angle section 0.85 into 2610 upon 19.6, and we have this value 113.19 millimeters. Then we have this as built up section. So go to table 10 and last row we have this as buckling class C. As it is buckling class C, so use table 9C. So we have KL upon R and FCD. So we have 110 and 120. For 110 we have 94.6 and this is 83.7. And from this we will get FCD equal to 94.6 minus 94.6 minus 83.7 upon 10 into base we have taken 110, so 113.19 minus 110. We have FCD value 90.35 Newton per mm square. Knowing this value, calculate value of PD. So we have PD equal to AE into FCD. Now AE we have 744. Now we have double angle. So 2 into 744 into 90.35. And by this we will get value 134.44 into 10 raised to 3 Newton. So we have 134.44 kilonewton, which is greater than 118.95 kilonewton. So therefore, okay. Therefore, provide angle 65, 65, 6 for member L8U7. Now we will go with another member. Now you can see we have this as first member. Second member L8L7. That is 113.94 tension. So member L7L8 or L8L7. So we have to design for 113.94 kilonewton tensile. Now we have to go to compression member. We have section compression member. We have section 7, and tension member we have section 6. And you have to go to section 6 and then see all this formula. So we have AG required equal to T into gamma MO upon Fy. And then we will get it as 113.94 into 1.1 upon 250. And we will have this area required 501.34 mm square. This is again double angle section, and therefore area required for single, AG required for single, and that is equal to 501.34 upon 2 is 250.67. But we are going to provide minimum section in truss generally 50-56. 50-56. And then we will select angle. So we will have this minimum angle 50-56, and we have area of this angle. Sorry, we have to now find out tensile strength. So now here we will go with only two due to yielding and due to rupture. So we have tensile strength due to yielding. Strength due to yielding. So you can see which will take more time. If you have question till panel point load, then it becomes easy. So now we have TDG, AGFY upon gamma MO. AG we have 568 into 250 divided by 1.1, and this comes 129.09 kilonewtons. Then we have second, tensile strength due to, so this is number 1. So we have tensile strength due to rupture at critical section. Due to rupture at critical section. And then we have this as TDN is equal to 0.9 ANC. NC means net area of connected leg. 0.9 ANC into FU upon gamma mm plus beta AGOFY upon gamma m. And then we will substitute the values that ANC, sorry, we have to first calculate. We have B minus NDH into T, and then we have this as B, we have 50 minus, we will consider 16 mm diameter bolts, and then we will have 18 multiplied by 6, and we have value of ANC 192 mm square. Now we have AGO, we have D minus T by 2 into T. So D we have 50 minus 6 by 2 into 6, and we have this value 282 mm square. Then we have beta, which is equal to 1.4 minus 0.076 W by T Fy upon Fu Bs upon Lc. So we are going to assume only two boards because load is very less. So assuming, and we have double shear, assuming two boards, and pitch, let us we will assume 70 millimeters. You can go higher also. So now then we have B, so therefore we will get LC equal to 70. We have only two boards. BS we have W plus WT minus T. And we know we have WT. Now we have 0.3 to 0.57 into 50. And now actually it comes in between. So I will consider 25 millimeters. So we have to assume it. And then if we will put these values, so we will get BS that is equal to 50 plus 25 minus 6. And we have this value 69 millimeters. So now we know these values. So now we will go for beta. We will substitute all values. We have 1.4 minus 0.076 outstanding leg upon thickness 250 upon 410, and BS we have 69 upon LC we have 70, and we will get this value 1.02. Now knowing this value we can find TDN actually. So we have TDN equal to 0.9 into ANC into Fu upon gamma ml plus beta AGO we have 282 into Fy upon gamma ml. We will get this value 122.05 kilonewton. This is for single angle, and TDN for double angle. We have 2 into 122.05. This will be 244.1 kilonewtons, which is greater than, we have value 113.94 kilonewton. Therefore, safe. Now these two I think sufficient. If you will get time, then only you can go for third. Otherwise, you can keep these two, will be on better side. But if time permits, you may go 1 or 2 marks if you will not go for third, that is tensile strength due to block shear. So now we will stop here only. Thank you. So this is all about your unit number 5. Now we will go with unit number 6 or 3. Thank you.